Good morning, students. This is next chapter, that is solid state. This is fifth chapter. We already discussed about gases in class 11 states of matter chapter, and also we discussed about liquids in solutions chapter in class 12. Now we are going to discuss about solids in this chapter. We know the particles are closely packed in solids, freely packed in gases, and loosely packed in liquids. And one of the definition for solids is the substances which have definite shape and a definite volume is also called solids. The substances which have definite shape and definite volume is called solids. So in solid state, the atoms or ions or molecules, nothing but particles, are arranged in three-dimensional manner, and these are arranged, they are closely packed. That means the attractions between particles are very strong, so that they are rigid. Rigid means they do not move from one place to another place. Next, based on arrangement of particles, arrangement of particles in solids. That means in some solids the particles are arranged in regular manner. Regular manner means the particles are arranged in orderly manner. In some solids the particles are arranged in irregular manner. That means irregular manner means randomly arranged. That is called irregular manner. So based on arrangement of particles in solids, they are classified into two types. They are crystalline solids and amorphous solids. Crystalline solids, amorphous solids. So here crystalline solids, this is the arrangement. That means here the particles are arranged in regular manner, so orderly arrangement. But in amorphous solids the particles are arranged irregular, that means randomly arrangement or disorder arrangement. Such type of solids are called amorphous. So the definition is the solids in which the particles are arranged in regular order or orderly manner is called crystalline solids. The solids in which the particles are arranged in irregular order or disorderly manner or randomly manner is called amorphous solids. I hope you understand the definition about these two. Here there are some more points regarding these two. They can be cut into two equal halves. That means because here the particles are arranged in regular manner, so we can cut them into two equal halves. Then also the particles are arranged in regular manner. But here the particles are arranged in irregular manner, so that we cannot cut them into two equal halves in this case. Next one, they have sharp melting point. This is the important point. Sharp melting point means here the particles are arranged in regular manner, so that when we heat that solids, then all particles melt at the same temperature. I repeat once again, sharp melting point means when we heat the solids, then the particles present in solid, all the particles present in solid melt at the same temperature, so that they have sharp melting point. But here they don't have sharp melting point because the particles are arranged in regular manner. So that means all the particles do not melt at the same temperature. Next one, they have long range forces. This is also important point. Long range forces means entire the solid attraction forces are same, because particles are arranged in regular manner. Particles are arranged in order, in particular order, so that the attractions between all the particles are more, because there is no chance of breaking of the attractions, because all particles are arranged in one order, so that attraction forces are same between all the particles. But here see, here the particles are arranged in regular manner, so that in some cases particles sometimes the attractions between particles are same, but in some cases there is a chance of breaking of attraction forces because the particles are arranged in irregular manner. Suppose if the arrangement is like this, in suppose the arrangement is like this, then what happens, between these two particles attractions are more, but between these two particles attractions are less, because here gap is somehow more. If gap is more, automatically attraction forces are less, so that these are called short range forces, because here arrangement is in irregular manner. Because of that, they have short range forces. Long range forces means entire the crystal or entire the solid, the attraction forces are same because the particles are arranged in regular manner. The next point is they are anisotropic and these are isotropic. Iso means same, aniso means different. So what is same? Here some properties are there. They are refractive index, electrical conductivity, thermal conductivity. When we apply these three properties to solids in different directions, different direction means x-axis, y-axis, z-axis, they exhibit different they shows different values in different directions. But here they show same values even though the particles are in irregular manner. So that is why these are called isotropic. Anisotropic means not same. That means when these properties are not same in different in x-axis, y-axis, z-axis, but these properties are same in x-axis, y-axis, z-axis. That is why these are called isotropic. These are anisotropic. These are experimental points. You just remember this. Next one, examples. Examples is for this crystalline solids. Most of these solids are in crystalline nature. Most of the solids in nature are in crystalline nature. Example in NaCl, AlCl3, NH4 twice SO4. That means all are salts. All salts, diamond, graphite, all are crystalline solids. But here quartz glass, that means glass, plastic, rubber, these are amorphous solids. These are the examples for amorphous solids. Here one important point is there, but generally we assume we feel that glass is a solid, but actually glass is a pseudo solid. Pseudo means false. That means glass is not a solid, it is a super cold liquid. This is very important point. Glass is a pseudo solid. That means it is a super cold liquid because after some time the particles which are present at the top of the glass moves slowly to bottom. Then what happens, the top of the size of the glass at the top decreases and the size of the glass at the bottom increases because particles are moving from top to bottom slowly. That means in glass particles are arranged in loosely manner. So that happens in which case? Liquid's case. But glass is a solid. So that glass becomes harder at bottom and its size is very less at the top. It takes nearly 100 years time. It takes nearly 100 years time. That means after 100 years, nearly almost 100 years, the particles which are present at the top of the glass move slowly to bottom. So the size of the glass at the top reduces and the size of the glass at bottom increases because particles move from top to bottom. So it has some liquid property. That is why it is called super cold liquid. Glass is a pseudo solid. Glass is not a solid. Glass is a pseudo solid. That is nothing but it is a super cold liquid. Next, here some more points are there regarding this one. That is, see, molten solids or liquid solid. Molten solid means if solid is heating, then if solid undergo heating, then liquid is formed. That is called molten solid. That is also called liquid solid. Here, if when liquids undergo, that means when temperature decreases in case of liquids undergo become solid by reducing temperature. Here are two points are there. Suppose if temperature suddenly decreases, that means suddenly cooling, then those molten solids become amorphous solids. Suppose when the temperature slowly reduces, nothing but annealing. When temperature suddenly become when temperature suddenly reduces, that is called quenching. When temperature slowly decreases, that is called annealing. Then crystalline solids are formed. This is important point. So amorphous solids formed from molten solids by sudden cooling, but crystalline solids are formed from molten solids or liquid solid by annealing. Annealing means slowly cooling. That means when temperature reduces slowly, then crystalline solids are formed. So this is all about crystalline solids and amorphous solids. Next one, next topic, there are some more types of solids. That is the type of crystalline solids. So based on the intermolecular forces between crystalline solids, they are again classified into four types. That means in crystalline solids, some attraction forces are there. Based on that, again they are classified into four types. We will discuss those four types now. Next topic is types of crystalline solids. Crystalline, based on the attractions between crystalline solids, they are classified into four types. They are molecular solids, hydrogen bonding solids, metallic solids, and covalent solids. This is the fourth type. Now we will discuss about these three. Then these four, that means what type of atoms are what type of particles present in these four, and what type of forces are present, and what about their melting point, and what about their conducting nature, and examples. If we discuss this topic, then this topic will be finished. So in molecular solids, in name itself molecules are present. That means in solids the types of particles are what? Molecules. Again molecular solids are classified into three types: non-polar, polar, hydrogen bonding. Non-polar means if covalent bond is formed between two same atoms, that is called non-polar. For example, H2, N2, O2, all these are comes under non-polar molecules. When those molecules are present in solid state, those are called non-polar solids. Here one more point is there. What types of forces are present? London forces. Already we discussed about dipole London forces in class 11 chemistry states of matter chapter. And here these forces are very less. That means the attractions between those particles are somehow less, so that their melting point is very less. Next, they act as insulators. That means when we pass electricity, they cannot conduct electricity. That's all. For these solids, examples are H2I2Cl2. Just now I discussed already. H2I2Cl2. Here for the dipole forces, HClSO2. Next, third category is what? Hydrogen bonding solids. That means those solids contains hydrogen bond forces. Here they are also, but compared to these two, these forces are somehow strong, so that the melting point is somehow better, somehow more than the previous two cases. They are also do not exhibit conductivity when we pass electricity. For example, ice and H3. These are the examples for hydrogen bonded solids. Next one, next category, metallic solids. In metallic solids, metal atoms are present, so that particles are atoms. In those solids, which type of forces are present? Metallic forces are present. Metals are those metallic forces are more strong compared to London forces, dipole forces, hydrogen bonding forces, so that their melting point is very high compared to these three. Then we know metals exhibit conductivity easily because of presence of free electrons. For that, examples are copper, iron, gold. So there are so many metals. We can sodium. All these are examples for metallic solids. Next one, ionic solids. Ionic solids. Why these are called ionic solids? Because those solids contains ions. So particles are what? Ions. Between ions, which type of forces are present? We know that is already what? Electrostatic forces of attractions. But these forces of attractions are very high, so that they have more melting point compared to metallic solids. Here one important point is there about conductivity. These are act as insulators in solid state, but they exhibit conductors in molten state or fused state. for these salt, all salts comes under this category: NaCl, MgSO4, aluminum chloride, aluminum nitrate, magnesium sulfate, magnesium chloride, ammonium sulfate. All these salts comes under this category because all those salts contain ions. And the last category, that is what? Covalent solids. In the covalent solids, particles are atoms or molecules. In the covalent forces are present. Its melting point is very high because of covalent forces, but they act as bad conductors except graphite, because graphite contains free electrons, so that it can exhibit conductivity. And for this example is diamond, graphite, boron nitrates, silicon carbide, that is also called carborandom. So these are the examples comes under covalent solids. These are about types of crystalline solids. This is next topic, that is crystal lattice or space lattice. Before that, I will discuss one point regarding metallic solids, that is a type of crystalline solids. So the point is, all metallic solids have luster property. Luster means shining, because of presence of free electrons. That means when a light falls on the metal surface, it gets reflected because free electrons are present. Therefore, metals has luster property. I repeat once again, when a light falls on the metal surface, it gets reflected because of free electrons. Therefore, metals has luster property. Luster means shining property. So that is about metallic solids. Now the next topic is crystal lattice or space lattice. Hereafter the topic is somehow different. We should imagine the topic hereafter. It is somehow difficult to imagine also. So listen carefully. Crystal lattice. See, for I just draw the structure of NaCl crystal structure. Its structure is like this: Na plus Cl minus, Na plus Cl minus. That means these are Na plus are present in alternative positions. Similarly, Cl minus also present in alternative positions. And here these ions are present in three-dimensional space. Here I draw just two-dimensional. That means two-dimensional means y-axis, x-axis. We can't draw in three-dimensional. In z-axis we can't draw it. So this is the structure of NaCl. Not only NaCl, any crystal structure is like this. That means the particles are arranged in 3D space. Here the point is, see, the particle which is present in 3D space is called lattice point. I repeat once again. The particle which is present in 3D space is called lattice point. So what is the definition of lattice point? The position of particles in 3D crystal. The position of particle in 3D crystal is called lattice point. Next, see, in this structure we can observe one point, that is Na plus Cl minus, Na plus Cl. That means this is repeating unit. Na plus Cl minus, Na plus Cl minus. Similarly, Na plus Cl minus, that means this is repeating unit. That repeating unit is called unit cell. That repeating unit is called unit cell. So the definition here is the smallest repeating unit in crystal structure. This is crystal structure. The smallest repeating unit in crystal structure is called unit cell. That is the definition of unit cell. And one more definition is there, that is crystal lattice. So what is the definition of crystal lattice? This is crystal lattice. So how can we say the definition? By using this one: the structure which is obtained when all the particles are arranged in 3D space. The structure I repeat once again, listen carefully. The structure which is obtained when all the particles are arranged in 3D space, that is called crystal lattice, that is also called space lattice. So here three definitions are there. First one is lattice point, second one is crystal lattice, third one unit cell. What is the definition of lattice point? The position of particles in 3D crystal. That means each particle is considered as lattice point. The position of particles in 3D crystal is called lattice point. What is the definition of unit cell? The smallest repeating unit in the 3D crystal. In the 3D crystal is called unit cell. Next, what is the definition of crystal lattice? The structure which is obtained when all the particles are arranged in 3D space. I hope you understand the three definitions: lattice point, crystal lattice, and unit cell. For example, take one wall. In that wall, bricks are arranged. So many bricks are present in wall. If you take any wall, so many bricks are present in that wall. Though those bricks are repeated, those bricks repeat entire the wall. So that one brick is considered as what? Unit cell, and that whole wall is considered as crystal lattice or space lattice. I hope you understand the example. Small brick is considered as unit cell, and whole wall is considered as crystal lattice, because that brick repeats enter the wall. That is why it is considered as unit cells. So that is about crystal lattice and space lattice. See, this is the structure of crystal lattice. So these are lattice points. That means position of particle in crystal is called lattice point. Next, this is repeating unit. There are so many repeating units like this. See, this is one, and this is also. See, this is also a repeating unit, and here also one more repeating unit is there. See, this is one repeating unit from here to here. This part is considered as one repeating. So here the point is, there are so many repeating units like that in any crystal, not only in NaCl crystal. Here you have to know one point, that is, this unit cell shape is just like cube. It is just like cube shape. So I will show one thing now. See, this is matchbox. We know that very well about this one. Here let us assume this is unit cell. Here this unit cell contains some positions. Now we have to discuss those positions. See, these positions, see, these are called corners. These points are called corners. Next, this is called face. This is face. Next, these are called edges. That means between two corners, that portion is called edge. Next, one more is center, body center. That means that is present inner side of the unit cell. So these are the positions of any unit cell. I repeat once again: corners, edge, face, and body center. So the particles which are present in corners, faces, edges, and centers also in any crystal. So here what we have to know regarding this one: how many corners are present in each unit cell? Each unit cell, not crystal. How many corners are present in each unit cell, and how many faces are present in each unit cell and how many edges are present in each unit cell and how many body centers are present in each unit cell. Here that is the important point. How many corners? First corners, see 1 2 3 4, next 5 6 7 8. So total how many corners are present? 8 corners are present in any unit cell. Next one, how many faces? See, this is one face, 1 2, next 3 4, next 5 and 6. So 6 faces are present in any unit cell. 8 corners and 6 faces are present in any unit cell. Next one, edges. Edges means what? Between two corners, that is called edges. See, this is one edge, 1 2 3 4, 4 edges. Back side also 4, 5 6 7 8, 8. Next, this is also edge, 9 10 11 12. So total 12 edges are present in each unit cell, not crystal, not space lattice, not crystal lattice. 12 lattice points are present in each, so 12 edges are present in each unit cell. Next, body center, that is present in inner side. So only one particle is present in at the body center in any unit cell. Only one particle, one lattice point is present in any unit cell. So that is about position of particles in unit cell. I hope you understand very well.